We're going to use VSEPR theory to help us understand shapes of molecules. So VSEPR is an acronym, VSEPR, and we're mispronouncing it, that's fine. Stands for valence shell electron pair repulsion theory. It's based on the idea that electron groups repel each other. It's a very simple model. It works pretty well. We need to be really clear about what is an electron group. So this definition is important here. A lone pair of electrons is a group. A single bond is a group. A double bond is one group. A triple bond is one group. A single electron is also one group. So we're going to look at the repulsions between electron groups on the central atom of a molecule. This theory predicts shapes based on spreading out the electron groups so they have the most amount of space. Maximum separation is minimum energy. So I think of this a little bit like the central atom is the Earth, and these groups are individuals that really don't like each other. So if you think about that, I think everyone's had at least one bad relationship, right? You think back about that, and it's like, imagine it times 100. You really hate this person, right? So if they're living on one side of the world, you just want to get as far away as possible. You're going to go the other side of the world. No chance of running into them. Repulsion, right? So these groups repel each other. So these groups are trying to get away from each other. This one isn't going to the other side because there's another one over here that's repulsive. And so they're doing the best they can, and they're going to spread out in this shape. That's the basic idea of VSEPR theory.
Do they have the same repulsion?
They do. Not all of the groups have the same amount of repulsion. Some of them are more repulsive than others, and we'll talk about that. So let's look at what happens when we have two groups on the central atom. So if we look at beryllium chloride, the Lewis structure is going to look like this. And this is one of those molecules that has an incomplete octet. That's the correct number of electrons, and everybody has 0 formal charges. And so that is the correct Lewis structure. We look at the central atom and we ask ourselves, how many electron groups? Well, here we have 2 single bonds. Each single bond is one group. So how do 2 groups or 2 people get away from each other? There's the Earth. They're going to go to opposite sides. Get as far away as possible. Maximum separation between the groups. This gives us an angle of 180 degrees. And then that determines how the atoms arrange, because we're looking at the electron groups repelling each other, and so that's going to put all 3 of these atoms in a line, and so we call this geometry linear, because they're in a line. This is what VSEPR theory predicts, and it's confirmed by observation. Let's look at CO2. If we look at the Lewis structure, we're looking at the central atom. We don't care about the lone pairs on these other atoms. We're just looking at the central atom. How many electron groups? Still 2, because a double bond is one group. The 4 electrons in that double bond are shared between the carbon and the oxygen. That double bond is stuck together. It can't separate and get away from itself. That's why it's one group. So we have 2 groups. Again, 2 groups getting away from each other is going to form a linear geometry. So if we have 3 groups, as we do in boron trifluoride, let's look at the Lewis structure real quick. Boron is another one of those small elements that violates the octet rule by having an incomplete octet. That's the correct Lewis structure. We look at the boron and we see there are 3 single bonds. Each single bond is one group.
If it doesn't complete the full octet rule, does it change the way it's...
No. The fact that this does not have a complete octet doesn't matter. This one's weird, but if we do formal charges, that's how it is. You can draw a Lewis structure where you have a double bond, but then you're going to have formal charges. And if you study the molecule, the 3 bonds are identical. If there was a double bond, then one bond should be shorter than the other 2, and that's not the case. So three things are going to form a triangle. Right, so we had a triangle going on here. This is called a trigonal planar geometry. So if you look at these balloons, they are in the same plane, right? They're not cooperating. I can lay them on the bench, and they lay flat. So this is a trigonal planar geometry, and the angle of separation here would be 120 degrees. They can't get further apart than that because there's 3 now. Let's look at formaldehyde. Here's the Lewis structure for formaldehyde. We're looking at the central atom. How many groups? 3 groups. Yes, carbon has an octet, but this double bond is one group. Because that double bond, both of those bonds are stuck between the carbon and the oxygen. They can't swing away from each other. So that's one group. This bond is a group. That bond is a group. So here again, we have 3 groups, but now they aren't all the same. One of them's different. This has a different atom, and this is a double bond instead of a single bond. So the double bond is slightly more repulsive than the single bonds. And we see that reflected in these bond angles. This angle here is a little more than 120, and this angle is a little less than 120. Because the hydrogens would rather be a little bit closer to each other so that they can get further away from that repulsive double bond. You do not need to memorize these exact bond angles. What I would expect you to be able to predict is that this one is greater than 120, and that this one is less than 120. And it makes intuitive sense. The double bond, you think, well, that's probably going to take up more space. And it does. And so it's going to push the other ones a little bit closer together. 4 groups. Harder to visualize. So here we have balloons, pictures of balloons in the slides, and I also have actual balloons here. And if you're doing this via YouTube, I would encourage you to get some balloons and blow them up and tie them together. So 2 balloons are going to arrange themselves like that. A linear geometry, just like 2 electron groups. 3 electron groups are going to spread out like this. They're going to make a triangle that's flat. Remember, the balloons are representing electron groups, not the atoms, the electron groups. If we add a 4th balloon, that is going to cause these 3 balloons to get out of a plane. They're not going to be in a plane anymore. So a tetrahedron is a shape like this where we have, come on, pointer. We have four equal sides. Each side is a triangle. There are 4 points. A cube has 6 sides and 8 corners, right? Yeah. This is 4 corners and 4 sides. The angles here are 109.5. That would be a good one to remember. That's in a perfect tetrahedron. What would be an example of a molecule? I'm so glad you asked. Here one is. Methane. So here's the Lewis structure for methane. There aren't any lone pairs on this one. The carbon has 4 single bonds to hydrogen atoms. Each single bond is a group, so we have 4 groups on the central atom. So for carbon, those 4 groups are going to arrange themselves like the balloons in a tetrahedron. And so the carbon here in the center is not down flat in the same plane as the hydrogens like it would be for a trigonal planar structure. These guys are pushed down together. They're a little closer than 120 degrees. They're 109.5. But all 4 hydrogens are separated from each other by 109.5 degrees.
Did you say what it was if there was, for the triple bond, if there was 2 double bonds in one sequence? Or is that not?
That's not going to happen,
Okay, so
pretty much.
We only did the 3 single bonds and then the double and 2 single bonds.
Yeah.
Thought I missed that.
Now, what if we had 5 groups? So 5 groups, you take your 4 balloons and you add 1 more balloon in there. And that is going to push the other balloons together a little bit. Do you want to see that in real life? Or are you good?
Now I see.
You see it? Okay. So we have 2 different kinds of positions here. We have the axial positions and the equatorial. So this would be like the North Pole of the Earth and the South Pole of the Earth. And then these in the middle are around the equator. There's a 90-degree angle between an axial chlorine and an equatorial chlorine. There's a 120-degree angle between 2 equatorial chlorines. This is sort of like a linear and a trigonal planar put together. The name of this is trigonal bipyramid because it's 2 trigonal pyramids stuck together. Any questions? 6. That would be this guy over here. Put a 6th one in, you get an octahedron. So now we have 4 equatorial groups with the 2 axial groups. But all of the bond angles are 90 degrees now. That's not true with the trigonal bipyramid. So this is an octahedron. It's an octahedron. There's an example of a molecule that does this. And so here the fluorine atoms with their single bonds are spread out. That's as far away as 6 things can get when they're all tied to this central atom. They're 90-degree angles. So let's determine the molecular geometry of carbon tetrachloride. You have to start with the Lewis structure. So we've got carbon and 4 chlorines. We'll try putting the chlorines around, bonded to the carbon. And then if you count up electrons and start sticking those around, you end up with something like this. And you can do the formal charges and they're all 0 and the octet rule is satisfied and it's all lovely. There's the Lewis structure. To determine the geometry, you look at the central atom. How many electron groups? 4. 4 groups. 4 electron groups. How do 4 groups get away from each other? How do 4 balloons? What shape do 4 balloons tied together make? Tetrahedron. So this is going to be a tetrahedral geometry. Any questions?